吃饱了吗？啊？吃饱了吗？啊？还没有吃饱。看起来也是。那他的副业啊？还有人吃一次。这是什么？还许发的。哎，我打算推迟一类一下那个货。怎么了？啊？为什么？没有啊，就是问一下有没有这个想法。对呀，为什么？因为写不完。写不完。没问题。昨晚才发现，现在写了3道题。对。啊？第一次讲的。第什么？老师啊？哎哎，后个星期，下个星期，后个星期，下个星期。哦，今天。没关系。我们追求的是无理由推迟，delay without excuse。技术。 I think Thm-MAT103. Hello. Okay, good afternoon to everyone. Later we can talk about assignment 2. Let me make some announcement first. So I put out a link suggested by Larry. This link here, if you can go and find it, it's in the top link of resources tab. Is the link proving apps for piano axiom and set theory. So if you don't know how to play around with axioms or you want to practice proof on set theory, right, you can click on the link, right, and then you go and play the game. So this is apps by Lean. Lean is developing tools, apps for proving maths. Okay, links are developed to do math proof, checking whether a proof is valid or not. Okay, why is the line so slow? Is that working? Right. So what's this? Okay. Yeah. So you can click on either of them, right? Or the first one. Yeah. So there are natural number proof, set theory proof, and I think this is the normal logic, is it? For example, we click into this number game here, and I set it to none so that we can play all games. This is how it works. I need to refresh it. Okay, everyone, huh? Yeah. So let's say where we want to go. So let's say any interesting one. Where's 2 plus 2 equal 4? You know? Addition. Around here. So let's pick either one of them. Okay. So there's a rules here, right? This rule is like if you fix a regular, meaning you need to go one by one. Otherwise, you can simply choose the level. This one, see. Relax. You can still play any level, but you can only use like the tactics up until from the start until this level. Oh, okay, okay. You stop after you go. Okay, thank you. Let's so for example this one. On the set of natural numbers, addition is associative. In other words, if you have A, B, C as natural numbers, and then A plus B, and then plus C is equal to B plus C, and then plus A. This is what we done in class, right? So you can try and prove using this tool here. It will guide you step by step what you can use, what you cannot use, and then how you get the whole proof done. Okay. So you need to start with the first game so that you know how to play, how to manipulate these apps. Okay, I won't show it here, but I'll just give you an idea what kind of question you have, and then it's really standard. The question here is what we did in class, what we have in the textbook. Okay, you can play the game. It's very interactive, I guess. I think. Okay, it's a quite a good exercise to do. Okay, yeah. If you found reading really boring, you can do this. Okay. Hello, Roland.
Yeah, we're just talking about this apps here. You can try and practice your natural number proof, set theory proof, logic proof using these apps. This is the apps by Lane. Lane is a tool that they developed to check the validity of mathematical proof. Yeah, so I put this link on Moodle already. It's the top one in resources. Yeah. Okay, you can have a play around it. Okay, so let's discuss one question that I think bothered some of you quite a lot. For example, or Vincent, right? In the class you asked. So there's one part of a proof that I said that for every x in R, okay, and there exists, for every x in R and for every n in natural number, there exists an smallest m in the integer such that x is less than or equals to m over n. First of all, you should think of it whether this sentence makes sense or not. I see. This sentence makes sense or not? Can you give me an example of this sentence? Yeah. How you find the smallest integer such that if I give you a rational number. So maybe I give you a real number. Maybe say 2.12. Okay? And then find me m and n that works, where m have to be the smallest, such that the inequality works. So part of learning this class, right, you need to turn these symbols into meaningful things. Okay, so I give you a task. So let's say I give you 2.12, and then maybe I give you 12 here. Okay, so what's the smallest m that works? Okay. Sure, you say first. Guess, pick one. M equals to what? No, smallest. Not 随便. 25, okay. You said 26. Okay, so there's M1, M2 here. So obviously 25 is the smallest among these two. But does 25 works or not here? What? Again. Okay, so you mean I just let's say I just take it to the other place, right? So instead of finding that, I find this, right? So what's this number here? What's this number? 12 times 2.12. NgeKieSeng, what's this number? 12 times 2.12. Again? 24.44. Okay, so does 25 works here or not? All right. Okay, so you need to pick 26. Okay, so we need to make this into a proof. How we find the smallest one? Okay, how to make this into a proof? Last time I explained in the class, how do I explain? Let's say x is greater than 0, right? So you start with 0, then you have maybe 1 over n here, and then you have somewhere x here, right? And then I say if you add enough, then you will pass by this x. This is how I explain, right? So how to make this into a proof? Okay, how to make this into a proof? Actually, you are quite close to the proof already. What you do, instead of considering this real number, what you're considering is this real number times the denominator. Okay, let me show you the proof now. Let me show you the proof. Remember this process, I will show you the proof. Remember the process, we find this m. Okay, so okay, make this become smaller. Let's keep it here. Okay, so how to prove this? So instead, we will consider nx. Okay, similar to what we have done just now. I multiply denominator to the other side. Okay, consider nx. We find some number some natural number that greater than nx. What's the property you can use? How to find a natural number? You want to find some so let me see here. So you should think that I'm trying to turn this question into like, so behind your mind, right? You should think that I am trying to turn the question into this. Okay, so how to find a integer that's greater or larger than this real number here? What's the property you can use? Archimedean property. Okay, so since consider nx. Nx is what? Is some real number. By Archimedean property, it says what? Any real number you can find a natural number that is greater or equals to x. Okay, so that is m such that nx is less than or equal to m. But not quite enough, right? Because we want the smallest one. Okay, we don't yet know whether this m is the smallest or not. So how to make this m a smallest one? Capital. Sorry? Sure, least upper bound. So how do we find this least upper bound? You need to give me a way to do it, right? Any way we can use them. Least upper bound property just say that exists. But can you find me one? Can we build a constructive proof or not? More constructive proof. Constructive. Of course, you can use this upper bound to say, oh, there's one. But can you make a constructive proof or not? How to really find the smallest n? Right. So I mean, go back to the example just now, right? So just now what? Just now 2.12. So 12 times 2.12. Let's say I said this number is 28. Okay. How does this 28 can give you 26? For example, how do you go from 28 to 26? Huh? How? Minus what? Okay, let's say you sorry minus double one. What do you mean double one? Oh, you mean minus one twice. Okay. Yeah, you could slowly reduce your bound. Okay. Right. You can slowly reduce your bound. So what am I saying here is so to find the smallest m z, okay, such that nx is less than m, what could we do? We could consider is this greater m minus minus one a few times. Okay, how many times you need to minus? For example, for 28, you need to minus 2 times. How about for 30? How many times you need to minus? 4 times. Okay, what does this mean then? This means that we can consider, for example, let's say p minus 1 times, okay, such that, what's this p doing here? P is the number of times, okay, minus 1 get added to M such that what? Such that NS is greater than M plus P minus 1. Okay. Why we can do this? Because we have trichotomy law in numbers. Okay, so you can keep minus 1. So each difference is either greater than the real number, equal to the real number, or less than the real number. Right? So now you start with a number that's greater or equal to nx. And then you take n minus 1. You ask yourself, n minus 1 is it greater or is it equal or is it less than nx? Right? Because for trichotomy, only one will happen. So the first instance, it happens that m minus p times minus 1 is less than nx. Then you know that the previous one is greater than nx. So what do I mean by this? For example, okay? For example, go back here. So just now 12 times 2.14, 2.12 is what? 24,544. Okay? So let's say I start with maybe Archimedean property give me 30 greater or equal to 2.44. How do I find 36? Okay, so I start 30 minus 1. Okay, ask yourself, is 30 minus 1 greater or equal to or less than 24.44? Greater, right? I want to go such that it is less than. Okay, such that it is less than and next here. Okay, so still greater, 29. Take minus 1 again, 28. Greater, 27. Greater, 26. Greater, 25. Smaller than. Okay, then I know that 26 is the one with smallest integer such that m over n is greater or equal to x. Does it make sense? Does it make sense or not? Any question about this proof here? Any question? So this is what I call a constructive proof because I give you a way to find m. Okay. If you just use the completeness proof, it will just say there exists one. But how to exactly find one is not given by the completeness axiom. Okay. Okay or not? Any question about this? Yeah, so I mean this result maybe seems quite obvious, right? But really for this course, okay, mathematical analysis, you really need to learn the way to spell it out. This proof here is what you need to learn how to construct in this course. Okay. First, you will explain this kind of a seemingly trivial or obvious statement here. Okay. Quite obvious, right? You can use all sort of way to find the smallest integer. But I write down a general proof here. Okay. I write down a general proof. A different proof, not just this one. This is my way. I just taking one minus 1. You can, yeah, depend on you. But you can. Okay. So what do we get here? So then we will get nx is less than equals to m. Okay. But what we want to get is x less than or equals to 1 over n. Okay, so we can just use the order, the consequence of order axiom that to get x is less than or equals to m. Okay. Yeah. Any question? Yes. Achievable. 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 PRB. Yeah, so right, I know last week we finished we just done our assignment 1. So assignment 1 and assignment 2 is like 1 week away. So how you guys goes with your assignment 2? Yes, start. Very slow. Take long question, okay. Start already. And then how about the rest? Not yet start. Some of you not yet start. Not yet download. Okay. So how about you go back and see, and then we will try and decide a deadline tomorrow. Is it okay? We go back and see, and then we try and decide the deadline tomorrow. And I usually my assignment is hard. I know it. Okay. So my way of doing assignment is different from the other lecturer. So my way is you can do research on it. Okay, you can ask people, including asking me. Okay, you can ask me, and then you can do research, but you cannot copy answer. Okay, you must write in your own word, and then you must cite whatever external reference you use. Okay, like website, other books, okay. But lecture notes no need to cite. Lecture notes you just use it. Whatever I state or prove inside the lecture notes, you just use it. Okay, only for lecture notes. Okay, so that's why lecture notes is very important. What I say in class is very important because this affects what you can use, what you cannot use. Okay, if you have to use something extra, then you need to provide the proof. This is my way of doing something. Hey, I think we got newcomers. Zeri, is it? Zeri. Yeah, so later in the rest, please come and talk to me about your assignment, how you gonna do it. And we have class representative here, so we have Jingsen. Jingsen, you want to wave your hand to him? Hello, Zeri. Zeri, this is your class representative. And then the other one is Sing. Yeah. So please get him into the group, and then yeah. So he just came today. Yeah, you can talk. And if you have any feedback, right, you can talk to both of them. Okay, if you don't want to talk to me. Seriously. Okay. All right. So any question or not about previous? Any other question about previous lecture tutorial? So I posted up tutorial solution already, right? So please, if you don't do, at least read. Okay, at least read them. Okay, tutorial is very important. So why I make this assignment so hard and so quite frequent, because this is the only way I can check you. Tutorial, I have no way to check you. Okay, but assignment is the way I check you whether you know something or you don't know something, what you're missing, okay, what you think is hard, like that. Okay. So tutorial really depend on you. Okay, please do it. I will provide solution. Okay, if you have question about tutorials, problems, you can also ask. We can also discuss in the lecture. Okay. So the main concern is you. Okay, you have to put in effort. Okay, and then I will put in effort. That's all. Does it make sense? Okay. Yeah, so in tutorial and the assignment, right, I put some question which is not mathematical. I'm not sure you read already. It's not like calculating something or what. It's reasoning. Okay, logical reasoning. I want to see whether you can do logical reasoning or not. You can see the question is like a bit like how to say 脑筋急转弯 like that. But seriously, you with your logical mind, you can even come up with this kind of question yourself, not just solving it. Okay. Okay. So this is the goal of this this kind of proving class. Okay, logical reasoning. Okay, you can prove or not. Can you reason well? Okay. Any question or not? If not, we're gonna start today's content. No question? Okay. Okay, so before I recall what's the limit definitions, I want to remind you something. Are these things familiar or not? This is last term we learned about this, right? Last long term. Thm-MAT's law of sequence. And then we learn squeeze theorem. Okay, hopefully you can recall all the examples. Okay, please recall those examples. And monotone sequence theorem or monotone convergence theorem. Right. So these are the slides I pulled out from last term lecture notes. Okay. So in this course here, we're gonna prove them. Okay, we're gonna prove them and see why they are true. Okay. Well, let's recall definition. Very important. Definition is like our kamus, dictionary kamus. Very important. You need to refer back. Okay, every word. So let AN be a sequence of real numbers. Right? So L in R is a limit, or is the limit. Last time I proved that the limit is unique, right? Is the limit of AN if what? Anyone recall? If n go to infinity and then n is close to L. How close is this? Okay, close is not enough. In mathematical analysis, we want to be precise. How close is it? How close is it? We want. How close? When we talk about close, what do we want to introduce? The difference, right? How we talk about the difference? Remember we give a symbol for difference. Difference of two numbers, which is very small. Epsilon, right? We want to talk about how close is it, okay? So if I give you, no matter how small epsilon I take, right? What happened? Not that we don't take epsilon to be zero, it's any positive one, positive epsilon, such that there exists a n, natural number n. So this n might be depending on epsilon. So I give you an epsilon, this n can change, maybe. Okay, such that what? For all the number that's greater or equals to the epsilon, n epsilon, what do you get? The term an minus the limit is less than epsilon. Is this enough? I need absolute value because I don't care whether an approach L from the top or from the bottom. Okay, so let me give you a picture here. So I have a L here, right? Okay, so let's say this line is L. My an could be approached from top and bottom, but as long as it is epsilon gap in the epsilon gap. As long as your sequence is in the epsilon gap here. Does it make sense? Yeah. All right, so let's prove some limits law then. Let's prove some limits law. I still remember Zhongyi used this as his calculus 2 assignment. You recall already or not? You recall? You don't recall? You can go back and check one, right? Go back and check. Yeah. Since you make this your project, right? I think you should be very pro on proving this already. Okay, so this limits law. So the proof of this limits law, right, form a very basic proof in analysis. So all other proof, for example, for derivative integration, remember how we define derivative integration? Those are defined using limits. Okay, so all the proof in differentiation, integration, all reduced down to proving this kind of statement. Okay, let me show you how we prove this. Okay. So in mathematical proof, right? Very important. You just remember one thing. What's the thing you need to remember? One thing. What's that thing? Circular reasoning already. What's the thing you need to remember in mathematical proof? The segment you want to prove. Okay, the goal you want to achieve. Okay, you must remember your goal first. Otherwise, you don't know where you go. Okay, very important. What's the one thing you need to know in mathematical proof? Yes, 不要怀疑，不要怀疑，我就敢说了，请你回答。Yes, remember the goal. Okay, okay, I remember the goal. Goal is very important. Okay, you watch FIFA or not? You watch football or not? If you put into wrong goal, what happened? Huh? What happened? Lose not only the mark become the other one, you know. Okay, 乌龙球. Okay, okay. So remember your goal. So for example, first one, what's your goal? What? Yeah. Okay, so meaning what? So meaning AN plus BN should be a sequence. Okay, this sequence should converge to L plus M. Okay, so let's put down our goal here. So let's write down proof. So I'll guide you step by step for this proof, and then you can do some other for exercise. So what is our goal? Our goal is for all epsilon greater than 0, that exists as n depend on this epsilon in n, such that for all n greater or equals to n epsilon, an plus bn is a sequence minus the limit. What's the suggestion limit here? L plus m. Okay, so L plus m here. And then take the epsilon is less than what? Epsilon. Okay. So you want to prove this. So how to prove this kind of statement? Universal quantifier. And how to prove this? Start with any epsilon, right? You pick an epsilon, and then you need to find this n, capital N, such that for all the little n greater or equal to n epsilon, this inequalities will hold. Okay. Think. Repeat what I said. Yes, repeat. I thought you should repeat what I said. You said repeat. Easy. Wait. What does this score say? Huh? What's this score? What? There's so many things here, you know.
Yeah.
Right? For every epsilon, you know. Yeah. And this is here. Okay. Yeah. Mm-hmm. Mm. Mm. Yeah. Yes. 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 Mm. Mm. Yes.
That's that.
Okay. Okay. Huh. So how we prove this kind of statement? Lỗ hở. Okay, lỗ hở. Right. 翻转经典. So how to prove this kind of statement? Universal quantifier. You need to prove for all epsilon. So how do you prove it? Epsilon, right? Okay. So we pick one epsilon. So let's pick one epsilon. So I just simply pick. Okay, pick idea. Okay. So the job here is we want to find the natural number that depends on this epsilon. How to find? No idea. Also no idea. Why you don't have idea? Because you need some assumption here. Okay, what assumption you know about AN and BN? Huh? AN and BN are convergence sequence. They don't just converge. They don't just converge, but AN converge to L and BN converge to M. So maybe we can write down what this two condition means then. Okay. So let's write down the two condition. By assumption, what do we get? AN goes, no, not AN equal to L, that one too strong. Okay, so what does this AN converge to L means? For every epsilon greater than 0, there exists a N epsilon. Okay, maybe I label this N with L. Okay, is it okay? We differentiate it such that for all N greater or equals to N epsilon L, we have AN minus L is less than epsilon. Okay, and Bn. What happened to Bn here? Same. Okay, similar. But maybe we have a different capital N here. So let's put it for M. So here is M, sorry. Right. Such that for all the terms after capital N, Bn minus M is less than epsilon. Right? So you see, you got these two inequality here. Okay. Can you fit this two inequality into the last inequality you want to know? Can you fit or not? How? How you break this long expression here into something short like this? Sorry? Absolute value. Add them up. How to add? What is add? Add what? Add these two together. How can you add two absolute things together? You mean this is true? Is this true or not? What is true is the triangle inequality here. You can split, split the term inside your absolute value, okay, which is less than or equals to the split sum of the absolute value. Okay, so So let's do some working here, right? So let's do some working here. So how to get to this stage of an plus bn minus l plus m, which is less than epsilon. Okay. So just now, what can we do? We can first rearrange the term inside, right? So what can we do? We can do an minus l plus bn minus m. Right? So this is the commutativity of real numbers. Okay. And then I can do associativity, right? It's associate like this. So if I associate like this, I can use triangle inequality here. Right? So what do I get if I get triangle inequality? So I get absolute value of an minus l plus absolute value of an minus. But just now I say that this is bounded by epsilon plus epsilon, right? So I get 2 epsilon here. Is it okay or not? Okay, why? Why not? Which epsilon in particular? Let's say our angle I want epsilon. Now is 2 epsilon. So what kind of epsilon I can be here? Epsilon over 2. So let's say I do it epsilon over 2, do it epsilon over 2, then I'll get 2 times epsilon over 2, which is 2. Sorry, which is 1. Which is epsilon. So which is epsilon? So why can I pick epsilon over 2, Roland? Can I pick epsilon over 2? Just now he only said epsilon. Can I pick epsilon over 2 here? Why? Why, Roland? Why can I make it epsilon over 2 here? Put it down. Okay. So just now, Ethan said what? Because this is true for all epsilon. You think true for epsilon means what? Let's say I put 0.2 here. I still can find this 10 epsilon. I put 0.1 here. I still can find epsilon. I still can find this natural number. Correct or not? But maybe the natural number will change. Doesn't matter. So you see, 0.2 works, 0.1 also works. So meaning epsilon works, epsilon over 2 also works. Why? Because this statement has to be true for all epsilon. Okay. And then what I mean about this natural number depend on this epsilon is maybe for 0.2 you have a smaller, bigger m. Maybe for 0.1 you have for 0.2 maybe you have a smaller n. For 0.1 maybe you have a larger n because you already get closer and closer to your limit already. Okay. So okay, so these are all my working. So what do I do here? So pick epsilon greater than 2. Okay. So consider n epsilon over 2. So let's see. Okay, so let's see by convergence an and bn. Okay. There exists n epsilon over 2 for L and n epsilon over 2 for M in N, okay, such that for all n greater or equals to n epsilon L, so should I split it? Okay, I think I should put like this for n greater or equals to n L or n greater or equals to n epsilon m, what do we have? We have the absolute value of an minus L is less than epsilon over 2, and absolute value of bn minus m is less than epsilon over 2. Okay. Okay. So remember what's our goal? What's our goal? Okay, remind ourselves what's our goal. Zhongyi, what's our goal? I show you already. Really? What's our goal? Not enough. Hey, which one? Which one are you reading? Go, go, go. What's our goal? Okay, so I already picked one epsilon, right? So what's my next job? What's my next job? Okay, I already picked one epsilon already. What's my next job? Find n, correct? Find n. Find n. How to find this n? What does this n have to satisfy? What does this n have to satisfy? At the one at the back, such that yeah. What happened? Okay, absolute value of an plus bn minus l plus n is less than epsilon. Okay, so we have a working here. Okay, we have a working here. So let me make this one smaller bit. Okay, we have a working here. So how to make this less than epsilon? Okay, we try to use the convergence of L and M to make it less than epsilon. Okay, so to make sure two of these converge, right? They converge at potentially different n. Okay, n L and n M. Okay, maybe this one need to converge for n equals to 10. This one, the other one need to convert for n equals to 20. So how do you confirm both of them converge within epsilon over 2? How? You need to choose the larger one. Okay, you need to choose the larger one. Right. So let me write down first and then we can discuss more with you. So we can pick n epsilon, okay, for L plus M to be the maximum of NL epsilon over 2 and NM epsilon over 2. Such that for n greater equals to NL n epsilon L plus M, what do we get? We get the calculation here. So the working here can move down now. So let's okay, so we get this working here. So first we use triangle inequality, and then second we use these the convergence of AN and BN. Okay, does it make sense? Does it make sense? A question or not? Okay, we need to pick the larger one. Why? Because maybe Bn haven't achieved, let's say the n for Bn is greater. Maybe before the n, the Bn haven't achieved the epsilon over 2 gap. Okay. So we need to pick the larger one. Get maximum of sense. Okay or not?
Right? Shouldn't the last line of the previous slide be
n larger than n epsilon of L and n larger than epsilon of L. Obviously, you put on.
Oh, because this is just talking about both of them. It's not talking together. Okay. Not related, not related. Not related. Yeah, not related. It's just that when I consider AN plus BN, then I have to consider them together. But for this line, I'm just talking about yeah, talking about the convergence of the two.
Then will the statement still work if one of them is still not?
All right.
Yeah.
So, or let's say this is true. If this is true, then let me think. If this is true, then maybe one of them not true. But if one of the other is true, then both of them should be true because these two numbers, either they are equal, either they are greater or to each other. I mean, okay, so there are two possibilities of this for these two numbers, right? So they could be equal. If they are equal, then this line should be true, right? Okay. If this one is smaller, let's say, okay, that one greater is similar case. So let's say this one is smaller. Okay. If it's smaller, right, then this might not be true. This might not be true. Okay. So I mean there's a statement problem here. True cannot imply false. Let me think. Oh, correct. I think you are right. So let's split this two then. I don't want to get into logical problem here. So let's split this two segment here. Okay. Okay. Move up. So there is a okay. So let's move this down. Okay, move this all the way down like this. This one greater than that. We have this and this one. Imply this. Okay, I think right in this way is better. Okay, just now I think got problem. Okay, I was just trying to like be lazy. Yeah, this is what I meant. Okay, so there's this natural number such that AN converges. There's this natural number for BN such that BN converges. This is what I want to say. Yeah. Just now I was being lazy and then I think it's the wrong thing. Okay. Yeah. Okay now. Yeah, this is what I want to say. I'm just trying to like write down the convergence statement for AN and BN. So here should be epsilon over 2. Here should be epsilon. Okay. Okay. So far, any question or not on this one? Any question on this one? On this one? No. Okay. If not, how about we take a break and then we will try and prove at least two of them for this limit law. And in the middle of this break, right, I want you to talk with your friend first. Okay, how are we gonna prove 2, 3, and 4? Yeah, try and talk to your friend. And I got some snack here if you want. Can keep you awake, jelly. You can take some jelly here if you like. And actually, I have some what's this? Oven baked bread. I think bread stick if you like. Yeah. Yeah, so let's take a break until 1:04. Okay, we will resume talking about the proof for limit law. Zuri, can you come here or I talk to you?现在是什么情况？你的 enrollment status 是已经包读这门课，几个？什么问题？可以仔细一点。嗯，本来是不打这门课的。
对
OK，然后对，没有，
毕业边边，
但是
你在嫌弃，
可以，
他嫌弃你耶！哎呀，都见，
对，没问题。但是我是说，如果要是有这样的情况，不是你可以先去上你要打的课程，不然的话你会在你必须要上的。可是我不知道你们看，但是我已经把你加进去了，不知道你们。你签了吗？我也有 recording，如果你要，
我就等待拿走。
我们上了什么东西或者什么等等，但是你是之前有拿过，哦，有拿过了，是睡觉。就你边看啊，OK，OK，没有问题。但是就是说，可能啊，我教的东西会跟他一些不一样，但是不是说不同东西啦，但是可能教法会不同啊，或者着重点不同，所以还是需要看一下我的 lecture note，他的 lecture note 也是是比较不一样，对，
你的作业
作业也不肯定不一样，因为
问题，
你问
这里底下是怎么写的？那这是第一个，
对，是这么写，对。
后面
没有啊，就是你要做的事情，for 这一题是你把它写成星座线，然后你给过后写成英文就可以。其实我没有这句话，其实你只要把这句话翻成英文就好，就或者说最后这句话，就这句话翻成英文就好。我没有说什么时候它Convergence什么时候，我只是来给他们一个概念说。我没有准确告诉他们什么是Convergence，只是我大概告诉他这句话跟这个有关，因为我们还没教这种东西，所以我这一题的作用是要让他们能够去理解一个
我就是不要人
逻辑，对，就是逻辑，纯逻辑吧。你可以不知道他在做什么，但是你可以去理解。所以你现在，因为我知道你比较迟，所以你的 assignment one 怎么办？还能够做吗？还是你能做啊 ？OK，能不能和 assignment two 一起交呢？你觉得？我本来是预定是这个星期四，但是看他们的样子，可能应该会 extend，会到下个星期啊，maybe。但是你觉得
如果我到现在，
好了，那两个都可以做吗？我是说都可以啊。那这样的话就定和定跟2一起交了，可以吗？应该我会 extend 到他们下个周的哪一天呢？我们明天再决定，可以吗？可以啊，OK。你联络他们了吗？你有进到那个这个班上有什么有什么普遍的这种问题啊？什么 如果你不要报单独的，你可以直接在然后里面马上的问题啊，
我爱自己，然后知道里面，
我
好吃啊！
要蘑菇
好，你很会享受哎，你真是会吃哦。是哎，这个好吃哎。我上次买的那个哦，有点漏风哎，
你
这个没有。
肯定觉得不好吃，然后再给我。
你这么这样讲，
你看
我真的不是，本来我这个买的本来就是这个礼拜拿来吃的。
这个不是这个不是影响赢了没？
不是，那个金宝讲这个蛮好吃，所以我才买啊。我还有买一个口味，他没有试过，结果那包漏风。
什么口味？
这个是 cheese，还有一个是蜜糖的。
我蒜的，我喜欢蒜的。
我靠，那个是 garlic cheese bread， 那个超级。
这是什么味道？
哇，不知道哎，怎么知道？一定不是自来水味道就对了。
椰吧，我去看我听到说，一整集都在扒这个，我第一次。
我当时我问1个小时吗？
确实，第一个人就是很难，做完1个小时也是一个啊。
这个
哇，我做完。
老鼠没钱，
没钱。
没钱，不是吃了几餐然后没钱了。
去哪里？
哦
，OK， 这样合理。
我猜测对。
每个人。
对呀，我猜测对。分手。没有一种。如果连麦嘛，
我没有吃到这个鱼。
如果麦嘛，
给我加死。
加死就拔到了。
厉害。
这你的透明对，不能只是发那种行为用来这样子。
我đang bị đề với bạn rất bị đề. Saya khai. Nếu khai吧，人家开吧。
哎，微微可以上。
我实地说一下。包成。
我一点都不敢做。
我已经
我感觉开始。这里我。
那个老大对发每两个都在领食。对，
太棒。
不然我们不然我们轮流带要不要？轮流带每个课一人准备1餐。OK， 下次啊，下一个。对啊，我们轮流带啊，下次啊。 不要太重也可以，我们先从小轻食开始，好不好？Next 轮流单，对。以后，我们选一场去 D6 上。好。没有。OK， 好，非常好，来，我们 restart 啊。So I keep mentioning about Zhongyi project why So you can go and try and dig out his project from last Buddha, okay, and see how he produced the proof. Okay, try and look back what's the project about. Okay, so for example, the second one, how to prove this? What's the statement you want to produce? What's your goal? Okay, what's your goal here? Okay, what's your goal? Like, try, check. Just that. 那什么？简单吗？简单耶。For all small n equal to implies what? Absolute value of CL taller than. Okay. So this is our goal. Okay. So our goal is to prove for all epsilon. So you need to pick an epsilon here. Okay. Let's try and do some working. So what do you know? You want to prove that this absolute value is less than epsilon, right? But what do you know? What's the assumption you have here? AN converge to L, meaning what? So for all greater than 0, again, this is a chart. You need to keep repeating until you sleep also, you know, okay? There exists an n epsilon in n such that n greater or n epsilon. Okay, let's label this special n here, okay? Label this special n such that absolute value of an minus L is less than epsilon, okay? So, I mean, you want to show this absolute value of CAN minus CL, right? How does this relate to AN minus L here? How does this relate to it? You can factorize the C. Okay, you can factorize the C. So how to factorize the C? So you should get what? Absolute value of C times AN minus L. Okay, can you do further? Okay, what can you do? Equals to absolute C times absolute of AN minus L. Okay, so, but what do you get here? I should get something like absolute C times epsilon, right? By 1 epsilon. How? I create a new epsilon. So I consider epsilon over epsilon C. Huh? For all C, yes. I mean, yeah. So this proof, right? Really, you don't just fix a epsilon, you should also fix a C. Because this statement should be true for all C. So let me see here. So we pick epsilon, we pick C, and we also pick epsilon. Okay, and then we consider epsilon over the absolute value of C, which is still greater than 0. Okay. Is there any problem here or not? This C is living in real. 0 is real. Can I divide epsilon by 0? No, so how? Then this statement false already, is it? This statement false or not? If C is 0, this statement false or not? False. To 0.
If C is 0,
Sequence of constant 0 converge to 0. False or true? Still true. But I cannot divide by 0. So that means I need to split into 2 cases. Okay, I need to split into 2 cases. So this one is case 1. So here is case 1. And maybe make it case 2, case 1 easier to say. So case 1, C equal to 0. And then case 2, C is not 0. Okay, C equals 0. Why I say it's easy? C times AN is really just 0 for all n. Right? N 0 sequence converge to 0. True or not? So it is true that the constant sequence of 0 converges to 0 times L, which is 0. Make sense? 0 is 0 times L in this case. Okay? Does it make sense or not? Make sense for the case C equals to 0? Okay. Okay. Can question for question? Case 1? No? Okay, so case 2 is our job just now. Okay, so how do we prove this? So by assumption, AN converge to L is true for all epsilon. In particular, I can fix a epsilon over absolute value of C. So by convergence of AN, okay, there exists an N depend on my limit and also depend on my sequence and also my epsilon, okay, such that for all the N behind this capital N here, what do I get? I get the absolute value of AN minus L is less than epsilon. Okay. Okay, not just epsilon, right? This is a special epsilon with peak epsilon of C. Absolute value of C. Okay. Then what's the N? Let's say, what is the N for our new sequence to converge? So what's the N of CL of epsilon? What's this N? What do I need to pick? Remember, my goal is I have an epsilon, I need to give an capital N, right? So what's the N I pick here? Such that the working will work. Okay, what's the N we need to pick here? Any idea? What's the N? We need to pick so that the working will work. So let me bring the working down here. So CAN minus CL, which is equals to absolute value of C times AN minus L, which is less than the absolute of C, which is equal to epsilon. Okay, so you need to find a capital N such that this inequality here works. So this inequalities here depend on what N. What N will work for this inequality here? When is this inequality here true? When is this inequality here true? Any idea? No idea? Okay, when is this inequality true? You need to go back and find when is this AN minus L less than epsilon over C? Where is it true? Where? Here. When is this true? Go back. When n is greater or equals to this capital N here. So you see, the whole inequality here really only depends on this inequality. So you need to make this inequality true, meaning you need to set your capital N to be just n of L at epsilon over the value of C. Okay, just use the same n will work. Does it make sense? Can or not? Use the same n will work. Okay. So you need to pick an n such that this thing will hold. So when does this whole thing hold? It is when the inequality of an minus L is less than epsilon over C, absolute value of C. But when does this hold? Only when n is greater or equal to this capital N here. Okay, so you pick this capital N be your capital N for Cn. For the sequence of CAN. Question? Any question? Don't simply pick. You need to pick that such that this inequality will hold. And then this inequality hold boils down to the convergence of an minus L. Okay. But previously, it depends on two sequences. So we need to pick between the two n. Okay. But now only one can work. So just take that one. Does that make sense? Okay. Question? Yes. Okay, we go back to the working. You mean this one, this one, this one, right? This one. Okay, yeah, good. This one follows from here. So here is strict. So here should be strict. Strict, right? Yes. So this one should be strict. Yeah. Okay. Yeah. Because this inequality here should come from this kind of inequality. Here is strict, so it should be strict. And then the last one should be equal. Right? Last one is equal. But yeah, you go through strict, then the whole thing is strict. Okay. Okay. Question? Yes. Say again. Go to n epsilon. Yeah. You can or you sure. If you want to make it consistent, you can put like this. But that's fine. Because it's just whether or not you have CL is still true. But it's just a clearer how to say, you make it clearer that this n works for the convergence of CAN. Okay, but for the statement, you don't need to put. So meaning this n here is depending on epsilon and also depending on your sequence. Okay. Any other question? So far, okay. Okay, so when you write down the proof, please write like this. For every epsilon, what's your goal, and then how you start, okay, how you fix your epsilon, how you pick your n, okay, such that the inequality works. So, can we go slightly faster? Can we go faster a bit? Okay, so let's go faster a bit. So let's prove the third one. Okay, so let's do the third. Okay, so to prove this, okay, we need to say that for every epsilon, there is a capital N such that the absolute value of an Vn minus Ln is less than epsilon. Okay, so I mean, really we can try and start with the working first. Okay. You don't need to write working in your actual proof, by the way. You just write the, you see. So there's a reason why I write this in green, because you don't need to prove this kind of working inside your proof. But this working will help you to find your n. Okay. So in the actual writing, you just keep the blue part is enough. Does it make sense? Okay. So the green part is just your working. 草稿. Okay. But in the actual writing, you need to write the blue part here. Okay. What you want to find, what is being fixed, what is being found, and then what is being obtained. Okay. Right. So working here, let's start with working here. Let's see what kind of n and epsilon we need to fix it. So you see, always when you see the convergence, right, you think of it as a minus. Okay. You want to converge to something, you think it as a minus, such that the difference getting smaller and smaller. Okay. So we consider the difference an, bn minus lm. How do we relate this? So from previous experience, right, we want to relate this to an minus l and bn minus l. So how we relate to the absolute value of an minus l and absolute value of an minus m? Any idea? Minus b and l. So introduce a lbn. Okay, so we introduce an lbn here. Maybe minus lbn plus lbn like this. This is one of the way. So what is Jack trying to do here? Hanwei, not Ethan, but the other Hanwei. Not sure, huh? Oh, you're not sure. Okay. Anyone can guess what is Jack trying to do here? Yeah, how to create? Break it, factorize it, right? We factorize it. So why we do this? Because you can see that there are two terms with bn, two terms with l. Okay, so we can factorize bn on one side and then factorize l on the other side. And what else can we do? We can now apply the triangle inequality here because we want to split sum. Okay, whenever we want to split sum, we can apply triangle inequality here. So what triangle inequality I can get here? The absolute value of an minus l times bn is less than, plus absolute value of l times bn minus m. Okay. Okay, so I can go further a bit. An minus l bn plus the absolute value of l times absolute of bn minus m. So I got epsilon here. I got epsilon on the other side because I know that an and bn converges. Okay. So what kind of epsilon I can take to make this into epsilon? Epsilon over bn plus epsilon value of l by this. Okay, maybe these two epsilon might be different, right? Let's set epsilon 1 and epsilon 2. All right, epsilon 1 and epsilon 2. And then finally we get something epsilon. Okay, maybe I just fix them first. Okay, just use epsilon. Okay. This. Sorry? Oh, you mean you want over 2. Okay, so over 2 because you left with epsilon plus epsilon, right? So you want to reduce it further. Can we do this or not? Can you do this or not? Epsilon over epsilon of Bn. What does this mean? Bn is changing. So if you divide like this, meaning you are not fixing epsilon already. Your epsilon keep changing. Every time you pass the n, your capital N will change. Okay. So it's really hard to control, because once you change your Bn, this Bn is dependent on N. Your capital N change. It's very hard to control. But here it's different. Here L doesn't change. So epsilon over some fixed number here is still some fixed number. The gap is fixed, but the gaps here is changing. Okay, so we don't want this. Okay, so we don't want this. We want some fixed number. We want to divide epsilon by some fixed number. Okay, so can I multiply by some fixed number or not? Here. Okay, can I bound this sequence here by some fixed number or not? What n? Sorry, Bn goes to m. Bn goes to m. Okay, so bound meaning I want to bound from where? Bound from top. I want to bound from top. I want to bound from top. Right. So let me see. Let me see. So okay. I want to bound from top. So let's say. So I ask a question here. So let me put a question here. Can I bound Bn from top? Okay, can I bound this? Sorry, I don't use m, later confused. So let's put some. Right, too many n. C, C, sigma. Okay, good, sigma. Okay, put sigma. Okay, can we bound like this? So, Ethan say, just take the limit, Take the limit and bound it. Is it possible or not? What if my limit is 0? Ding, 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 ding. My limit is 0. Right, Bn go to 0. Go to 0. Right. Separate case. Sorry? Yeah, this the other case. How about you alternate between the sequence and maybe okay, let's do something weird here. So maybe you like this, and then still converge to 0. Okay, so how you bound this? How you bound this? It's from this picture, from this picture. If I have this kind of convergence sequence, right? What number can bound the sequence? The term of the sequence. Which one? Which term here can bound the term of the sequence? Which number is the greatest one from this picture here? Which one is the greatest one? The first one, yeah. Right. This first one is always greater to the everything behind. Okay. But is this true for all convergence sequence or not? Is this true? Is this true or not? Maybe I can do some stupid thing, right? I introduce the first term as like this. So which terms will bound my sequence? All the terms in my sequence. In this case. The second one. So it changes. Not always the first one. Right? So is it true that we can always bound convergence sequence? Not true, Jet said not true. Is it true? Okay, so I'll put the lemma here. Okay, lemma. any convergent sequence is bounded. Every convergent sequence is bounded. Okay. So precisely, what does this mean? So we want to put it into a mathematical statement that we can prove. So precisely, if Vn is a sequence which converges to a limit m, then what? Then there's this a k, okay, greater than 0, such that the absolute of Bn is less than equals to k, okay, for every n. Why does this make sense? Why does this make sense? Look at the picture again. When you say you want to converge to a limit, right? What happened to the far sequence? What happened to the tail of the sequence? It needs to be within some epsilon gap with the limit. Okay. So they are very close with your limit already. Right. Does it make sense? Okay, they are really close to your limit already. So there are really only finitely many of them, which is far away from the limit. Does it make sense? Let me draw a picture. When I say epsilon gap, you should imagine something like this. Around the limit. Okay, there's an epsilon like that. Oh, let me draw this straight. So there's some epsilon gap here. Okay. For all the tails of convergence sequence. Because if you want to converge, all the n behind the greater n have to be epsilon between the gap. So how do you find the largest guy? There are really only finitely many of them to consider, right? Does it make sense or not? Does it make sense? There are only finitely many of them you need to consider. Which one is the greatest one? Sense? Any question? Are you understanding what I am talking about? If not, please ask. Very important. This concept is very important. Because this is about the tail of convergence sequence. The tail of convergence sequence is always epsilon close to your limit. Okay? Outside epsilon, there are only finitely many of them. Okay? Does it make sense? There are finitely many of them. If you say that word away from epsilon, still have infinitely many of them away from this limit, then your sequence is not converging. Okay? Contradiction. Okay, so there are only finitely many of them is away from the epsilon gap here. Okay, so let's see how to prove this. Okay, let's see how to do this precisely. So let's put a proof of lemma. So really, we can just consider the gap to be epsilon equals to 1. Okay, we just consider this. Okay, consider epsilon equals to 1. Then, since Bn converges, okay, since Bn converges, then for any n, so there exists what? I fixed epsilon already. There exists an n, capital N, depend on this epsilon, okay, such that for all n, so let me write like this, since we only have one variable here. Like this, greater or equals to n1, okay, we have what? Absolute value of Bn minus limit is less than 1. Okay, which means what? Which means what? Which means what? What does this tell me about absolute value of Bn? It is less than or equals to absolute value of m plus 1. Does this make sense or not? No. No, man. No, this doesn't make sense. Make sense?
It's only true if n is bigger than or equal to.
Sure. Yeah, sure. Let's put this in. Sure. Okay, but I mean, my point is, does this inequality above here implies a lower inequality here? Is it true? True enough. Okay, so how do you think about this? Prove that. Or maybe prove that A minus B less than C. Okay. So for C positive, okay, and then for all A, B in R implies absolute value of A is less than or equal to S of B plus C. Okay. Okay. But from the picture, how you see it? From the picture, how you see it? From the picture, how you see it? From the picture. So this one is algebraic proof. Please prove it algebraically. So prove algebraically. So in picture, how to see? Geometry, intuition. So in geometry, let's say m is greater than 0. Okay, let's make our life easier. Then we'll get Bn minus m less than 1 implies absolute value of Bn is less than or equal to m plus 1. Right? Okay. So Bn minus m, how should you think about it? So you should think about, so last time I told you, right, whenever you see this inequality, right, put them into a number line. Okay. So if I say absolute of Bn minus m is less than 1, meaning what? Between Bn and m is, so either you are going from here plus 1, right? Let's say our angle do like this. So here is plus 1, here is minus 1. So your Bn lives somewhere here. Okay, Bn here or Bn here, maybe n1, n2 here. Okay. So does this implies that the absolute value of Bn is less than or equal to m plus 1? So your absolute value of Bn is always less than m plus 1. Correct? No matter you are at the top or you are at the bottom, you are still less than m plus 1. M plus 1 is where? M plus 1 is at the top here. Does it make sense? Okay or not? You see, no matter you are away top or bottom from m by 1, you still less than m plus 1 here. Okay, so this is one case for m greater than 0. M less than 0 is kind of similar. It's even kind of similar. Okay. So try and produce algebraic proof. Okay, using the definition of absolute values and also the property, okay, about this absolute. So you see, the intuition is like this. Does it make sense of this intuition or not? Make sense, NgeKieSeng? Make sense? Okay. Can you see it? Can you guys see it? If you can't see, you just ask. Ivan, can see or not? And okay. So this is the case for m greater than 0. You can try m less than 0, m equals 0, and you can see what happened there. Okay, so we have this property here, and then, so are we done yet? Okay, can we just choose capital M? Just choose absolute M plus 1. Can we just choose that number there? Can we just choose that as our bound? As our bound name. Okay. Can I choose that as my bound or not? Can I pick like this? Maybe not enough, right? Because just now, like what I said, if you have picked this bound here, okay, and then you pick the largest one, maybe it's this guy. Okay, maybe it's this guy is the largest one. How about the previous guy? It could be larger then. It could be larger, right? So you need to consider all the possibility before. So you need to take actually the maximum of all those finite guys. So what are those finite guys? Those are B1, B2, B3, all the way up to B of n of epsilon equals to 1. Okay, this is enough. Okay, it should be enough. Okay. Actually, when n equals to n epsilon 1, right, is already smaller than the smaller or equal to capital M plus 1. So to be precise, we can take one smaller. Okay, all the finite guy. All the one that's not within epsilon, yeah, with the limit. Okay. So you can see that this capital M plus 1 here is your limit plus absolute value of your limit plus the epsilon get 1. Okay, away from the epsilon get 1, you still have all these finite terms to consider. And your term is bounded by the maximum of this set here. Again, maximum of this set. So let me put here max. Okay. Makes sense? Any question? Question? Any question? Any question about it? No. No. Okay. If not, then we found a bound for this Bn here. So let's return to our case here. So I said that this K could be useful here. Okay. Okay, could be useful here. How useful is this? Let's say I bound this Bn, let's say I take this epsilon to be epsilon over 2k. What happened to this term here? This k is always greater or equals to epsilon value of Bn. So meaning when you divide it, what do you get? Something less than 1. Okay, so it could be strictly less than epsilon over 2 plus epsilon over 2, which is still epsilon. Okay. Makes sense? Okay. So let me point out to you that this, let's use the other one. So this guy, this cancellation here is always less than 1. Okay. Does it make sense? Okay or not? Okay. So you see, you want to have two convergence here, right? You want to have two convergence here. And then this two convergence might be depend on this 2 epsilon here. So what's the n you need to pick for an times bn to converge here? What's the n you need to pick? Go a bit faster here. So what's the n you need to pick for your an bn to converge? So there are two convergence happening here, right? So how you fix your capital N here? Minimum? Maximum? Maximum of who? Maximum of who? N of convergence of AN, okay, with epsilon over 2k, right? The k that we fixed just now. And then N with the convergence of M with epsilon over 2 absolute value of M. Okay. Does it make sense? So the k here comes from the bound of Vn by the proof just now. Okay, so you pick this N such that both of them will stay within the epsilon gap that we pick. Okay, so that this two epsilon will hold. Does it make sense? Any question? Question? Yes, definitely. You have to consider when L is converging to 0. Okay. So you need to consider where L is converging to 0, because again, we are dividing by 0 again. Okay, we are dividing by 0 again. So so what to do here? Of course, here K also divide by 0, right? So K here also divide by 0. Could be divided by 0, right? You could be bounded by 0, right? But something that can be bounded by 0 also bounded by 1, for example, 2, for example. So just use some larger positive number in that case, because you just act as a bound for Bn. But L you cannot change. Something that converges to 0, you cannot say it converges to 1 or 2 or 3, right? Okay. So let's say L converges to 0. What happened to this statement here? If L converges to 0, what happened to the statement? AN, BN will converge to 0. Okay. So AN and BN will converge to 0. Okay, so let's go down. What happened to this inequality here? So let's do calculation. Okay, so let's say, so case 2, so L equals 0. Okay, what happened here? So we want to show that AN, BN is less than epsilon. For every epsilon, greater than 0, there is an N epsilon such that for all N. Okay. Can we do this or not? If L is going to be 0. Let's see, can we go easier? Should be easier, let me think. L go to 0. Okay. So I think we should have easier stuff here. So if AN go to 0, so you see, so here, look at the working here. Okay, we try to do inverse engineering here. Let's try and look at the working here, and then you sub L to be 0, right? What can you see here? So I can go for AN, BN to first line here, right? Because you can just minus 0 times M. Right or not? Does it make sense? And then I go through the same thing up to here. Here, what does this term here? This is really just 0, So this guy shouldn't appear. So that means what? That means the convergence of Bn doesn't involve here. Okay. Doesn't involve in this calculation. So what you need is the boundedness of Bn and the convergence of An here. Okay or not? Does it make sense? Does it make sense? Okay. So really, when you do it for L equals 0, this term here, you don't need to care anymore. You can throw away this term. You just look at the convergence of An is enough. Okay, I will write it out clearly in the lecture notes. Okay, but please get what I said first. I will write out clearly. Okay, does it make sense? Okay, so if L is 0, right, this term disappears. So you don't need to really care about the rate of convergence of Bn. Okay, but the convergence of Bn still help you to bound the Bn terms. Okay, still need the bound. Okay. Does it make sense? Make sense or not? Okay. A question? Okay. So I spent like 2 hours, right, going slowly about this proof. So I want you to really get what this proof is doing, because this proof is serving for the foundation for the proof for all differentiation and integration. Okay, you must know this first. Okay, otherwise you definitely will get lost later. Okay, everything for differentiation integration should come back to this limit law. Okay, so you must really familiar 倒这倍都要 ，OK， 倒这倍，正这倍已经没有用了，现在要倒这倍，OK， 正反倍 ，OK，OK 了 ，Does it make sense? Okay, so I will let you to do exercise for part 4. Okay, I will write down the proof. I want you to write down the proof. Okay, for part 4. Okay, so this one is homework. Okay, must know this is the crux of this course. 这是精华。Okay, if you don't get this, that means wasted for this course. Okay, so really, what's this course about? Is really this one. Okay, limit of sequence. Okay, this is a very important thing. Limit of sequence. Okay or not? Okay. Okay, so should we take a break again? Let's take a break and then we will return with a monotone convergence theorem. Okay. So when I go through this theorem, right, this law, right, because we introduced in calculus 2 before, so sometimes I will skip examples. So if you want examples, go back to calculus 2. Okay, try and find how we use this. Okay. So we'll focus on proof and then how we use this in general, proof question. And so let's take a break until 2:03. Are we ready? Ready? Ready for the last hour? Okay. Okay. Last hour, last boost before finish. Yeah, last boost. So yeah. So you can see that I put some references in Moodle using abundance of proof examples, right? You can click on the book. So actually these links are the books. So let's say we click on this one. Right, we click on this one. Then go to this proof here. And you can look for something like so proof in number theory, combinatorics, calculus. So go and find proof in calculus. Okay. So if you go and find proof in calculus, you will see something like this. Limit of sequence. Okay. So this is what we were going through for so they have like a summary. So you can do a very good revision here. And most importantly, they have this kind of examples. Okay, like 1 over n converges to 0. This is what we have done in class. And you can see that they have slightly different proof, maybe using the floors or ceiling stuff. Okay, you can have different sequence converge to different limits. Okay, see how they prove it using epsilon and n. How to find n? Okay, depend on epsilon. And there are all sort of examples here. So I would encourage you to study this, okay? Because why I know this? Because I also gone through your process, first time seeing epsilon and n. That's the first time I feel like I'm failing in my maths. You know what this feeling is? For a person that always get 100 in maths. You get what I mean? You get what I mean? You know what this feeling is? You know you are very good at one thing, but that thing is the thing become one thing that you don't know. When I first learned this analysis, this is the first time I feel crisis in my mathematics. You know, crisis, serious crisis. I'll tell you a story. My undergrad first year, right? Our maths is doing 2 parts together. Analysis and linear algebra. It's not like you guys separate, right? We mix together. We only have one maths course in first semester, second semester. So that semester is like doing linear algebra and analysis together. So how do we do that? Each week we have 2 hours on analysis, 2 hours on linear algebra. So 4 hours of lecture plus 1 hour of tutorial. Okay. And after the analysis exam, right, we do the exam together as well, like 3 hours like that. And I feel like I'm failing the analysis part. Although I can get like full mark in linear algebra, but I'm failing analysis. First thing is I don't understand what the question is asking. You know? Why I feel this? Because in our high school mathematics, right, the question is predictable. What does it mean by predictable? The pattern is the same. I just change number. As long as I know the working. Right? But go to university level, right? Question is different. Working is the same. So you don't know put what working into that question, you know. Working is the same, but problem is different. But the problem is I don't know put what answer into that question. So I don't know how to write. So this is the point that I really focus and stress on in my class. You must understand the question. Okay? To understand the question, you really must understand true definition. That's the only place you can understand. If you're going to understand true examples, it's really hard. You know why? Because true examples, right? You might not be using definition. You might use your own definition, your own method to understand. But maybe that method is wrong. It's not applicable to all cases. You know, then this is the place I can trick you. Because you always forgot this case. Then I put that case into exam, you don't know how to do. You get what I mean? So you need to understand a concept holistically. Okay, every cases you need to consider. Only you can do by definition. Okay, if you still want to do by examples, it's really hard. It's really hard, harder than definition. You know why? Because how do you know that the example you haven't exhausted? 你怎么知道你已经考虑完所有的情况？ You get what I mean? 所以你怎么知道你考虑完的情况，就是要回去 definition。definition 说要考虑什么？你考虑了吗 ？definition 说考虑什么？你考虑了吗 ？Okay, so definition is your destiny. Okay, is your destiny. Okay, this is why we learn maths. Must have definition. Okay, everyone must start with the same definition. Okay, if you're gonna start with different definition, then we are living in different world. Okay, we are living in different world already. So for here, for now, we start with definition of sequence. And actually, this book is actually quite good, you know. There are proof in group theory as well. So if your AA got problem, don't know how to prove, I also can learn from here. This book contains all the standard question. Okay, you can see the pattern. Okay, and then most importantly, refer back to definition. Okay, don't just study examples. Okay, go back to definition, see how this example demonstrates the definition. Okay, definition must be the most important, put in the most important place in your heart. Okay, that's definition. Read examples with definition. Okay. Okay. So not just this book. All the book I said abundant proof examples got similar example and working. Okay, you can see how they do it. Okay, maybe slightly different, then you can see that why are they different, why are they acceptable, something like that. Okay, so if you meet the wall, okay, 撞到南墙了，很难 go to this book. Okay, go to this book, or you come and ask me. Okay, all this book 1, 2, 3, 7, 8, 9, 10, 11. This book very good. Okay. Maybe sometimes I will get questions from there as well. So it's really good, this book. You see, when is this book being written? 2021, 2018, 2016. I do my degree at 2014. So there are not many modern reference for this proof here. Okay, we learn it in the hardware. Okay, but now they already like somehow they know that student will get really hard understanding the proof, so they try to collect all these similar proof for you to compare and understand. Okay, but still, what is the most important thing in learning maths? What's the most important thing? Logic, definitions. Okay, definitions, very important. Definitions. Okay, get definitions first. Only you have logic. Otherwise, how you put the logical statement? You don't have definition yet. Okay, definition is most important, and then logic. Okay, and then 你可以推导一些东西。But need to start from everything start from some definitions. Okay, everything start from definitions. Okay, definitions. Always keep definition in your mind. It's like a dictionary. Okay, so since we talk about definitions, some more definition is coming in. Okay. So we want to introduce monotone convergence theorem, right? So let's just quickly recap what is the monotone sequence means. So what's the monotone sequence? If what? If it is either non-decreasing or non-increasing. Okay, non-decreasing or non-increasing. But what does these two words mean? Okay, what does these two words mean? Yes. Oh, sorry. Thank you. So either non-decreasing or non-decreasing. Okay. So non-decreasing. Okay, so what does these two words mean? So for the first one, non-decreasing, so meaning it is not decreasing. Okay, so if it is not decreasing, what can happen about AN? AN plus 1, the next term should be always greater or equal to the previous term. Okay, it's not decreasing, right? So it must be greater or equal to the AN. But on the other hand, if it is non-increasing, meaning it is not decreasing, sorry, non-increasing means it is decreasing. Okay, so what does it mean by decreasing? AN plus 1 have to be less than or equal to AN. Okay, okay. So you're comparing the term with the next term. Okay, and just now we speak about bounded, right? So let's put the boundedness precise. So a sequence is called bounded above. So okay, so let me just define like what we did for monotone. So a sequence is bounded means what? Means you can bound from two ways, right? Mean if it is, so here is if it is bounded above and bounded below. Okay. So what does bounded above and bounded below means? That is for every n in n, there exists a upper bound. So there exists m in R such that all the terms an is less than or equals to m. This one is bounded above n. For every n in n, there's this, let's say, small m in R such that an is greater or equal to m. So here is respectively. Okay. One is for bounded above, the other one is for bounded below. All right. This is enough. Yeah, I think this is enough. Okay, so recall what is the convergence, monotone convergence theorem says. So monotone convergence theorem. Anyone remember? Huh? Every monotone, not just monotone, but bounded, rebounded monotone sequence. These are the two adjectives we introduced, right? What we want them to happen, they converges. Or even strongly, right? Every bounded and ultimately monotone sequence convergence. What does it mean by ultimately monotone sequence? Not strictly. Ultimately means like at the end, right? So at the first few turns, it might not be monotone. Okay, it might be jumping around. But at the end, it becomes monotone. Okay, so you should imagine something like maybe it is not monotone at first, but somewhat monotone at the end. Like that. Okay, still converges. Okay, the statement is still converges with boundedness. Okay. So this will be described, not described explicitly, but implied by the proof later. Okay, will be implied by the proof. Why? Because I can disregard the first few terms and talk about the convergence at the end. Right? Because what's convergence? Convergence is about the tail of the sequence. You need to look at small n. Since there's small n. What does small n mean to you? Small n greater than the capital N. All the small n behind the capital N. So it's the tail. Okay, 尾巴. Okay, no? Sequence of 尾巴. So tails of sequence is very important for convergence. Okay, let's prove this. How to prove this? How to prove this? If you have a monotone sequence, right, and then it is bounded, okay, how do you find the limit? How do you find the limit? You find the limit. You find the limit. I'm not sure you guys still remember or not. I'm not sure I included in your test. Like I test you, right? I test you like if I have a monotone convergence sequence. Let's say it is bounded by some limit like this. Let's say it converges to 0. Okay. And then it has bounded like by -1. Does it converge to -1 or not? Does it converge to -1? Huh? Does it converge to -1 or not? Yes or no? Let's say this one is 1 over n. Okay. No, quite far, right? So how do you find this 0 then? Sorry. Put this term into a set, then this set, this sequence is non-increasing or non-decreasing? Non-increasing. Okay, put into the set and then
sequence is bounded below.
Hmm.
You can use the same term to say that this set is also bounded below.
So this term is bounded below is because of the boundedness, not about the monotone. Right? Monotone can keep decreasing. You can bound below by this term, right? But if you see from the previous knowledge, right? If I bounded below by what? So what's the greatest lower bound? What's the infimum of this set here? 0. Okay. And we want to show that this is the limit of my sequence. So you need to solve the business of epsilon n. Okay. But this infimum exists is very special, you know. Why the infimum must exist? Because it is in the completeness axiom. So the existence is given by the completeness of R. And then you need to show that this is the limit. Make sense? Okay. So let's do it. Yeah, let's do it. If you still don't understand, so look at what I do. Okay. And then try and make sense of it. Still don't understand, then ask. All right. So every bounded monotone sequence converges. So let's say there are a few cases, right? So let's without law for generality. Okay. So we just consider this cases. Suppose AN is a sequence which is non-decreasing. Okay. So non-decreasing meaning it is increasing. Okay. So if it's increasing, because it is bounded, right? It is bounded above and below. So we consider it is bounded above. It is still bounded below, but bounded aboveness will give us the limit. Okay. So if it is non-increasing, you can use the other one. You can use bounded below property. Okay. So let's see what we do with this bounded above property here. So like what Larry said, we just consider a set of AN. Just consider this set here. So we don't see it as a sequence now. We see just a bunch of numbers. Okay, this bunch of number got what property? It is bounded above. Okay. It is bounded above. What does it mean by bounded above? Like, is this a capital M that is greater or equal to all the terms? So by completeness, and this is true. So by completeness axiom, the sup exists. Okay, sup of A exists. Okay, so there's a lowest upper bound for this set. So we want to show that this is actually our limit. Okay, we want to show that this is our limit. In particular, what? So remember, we have few equivalence definition of upper bound, right? So what's the one of the equivalent definition? For any epsilon greater than 0, okay, there exists an element, let's say called A epsilon, depend on epsilon, in my set A, such that this term here is greater than A. Okay, cannot greater than A because it's already this upper bound. So meaning greater than A, a bit away from A. Okay, minus epsilon. If you are a bit away from A, I can find something in my set that is greater than A minus epsilon. Okay, how am I using this here? Okay, so actually I'm using this epsilon here to find my capital N. So by definition, A, okay, this term here is in A, right? But everything in A is realized by some N. Correct? You can write it as AN for some N. What's your A? A is A1, A2, A3, A4, A5, A6, right? In particular, this epsilon is one of them. So meaning there's a capital N that realize this number here. Okay, so you can see that I'm trying to build up this capital N here. I'm claiming that this guy will help me to show the limit. Okay, so let's see how we show this. So by the non-decreasing condition, okay, what do we get? So I'm trying to hinting that this is the capital N I need for my limit. So what do I need to show? So for any N greater or equals to N epsilon, we have what? AN, which is greater or equals to this AN epsilon, right? Because this is non-decreasing. Yeah, non-decreasing. So you are increasing, okay? Increasing or equal. And by this least upper bound property here, we have AN epsilon greater than A minus epsilon. Okay. So we have one inequality here. AN is greater than A minus epsilon. Okay. And also what? And also, AN is in A, right? Okay, so in particular, we have what? This AN is less than or equals to sup A, which is A. Okay. Which is equal to A. Meaning what? Which is equal to A. Also less than A plus epsilon, right? Okay, so altogether we have what? AN is less than A plus epsilon is greater than A minus epsilon. So what is this? Absolute value of AN minus A is less than epsilon. Okay, so this is what we want. What is the capital N? the capital N is this N epsilon given by the property of least upper bound. Okay, so this implies that for any N greater than capital N epsilon, AN converges to A. Okay, right? So we are using the property of least upper bound to prove the convergence of the sequence. So you can think of it like previously we have just a set with bounded above set, and then we found the sup A. But now we try to take a sequence of this number and then find the least upper bound. Okay, we make it into a sequence now. Okay, and then it is non-increasing, decreasing at the same time. Okay, does it make sense? Does it make sense or not? Okay. Okay. Let's see. Okay, does it make sense for the proof? Does it make sense? Any question for the proof? Question? Question? No? Okay. If not, let's prove another one. Let's prove another theorem. Let's prove a theorem called the nested interval theorem, because this will be very useful for the subsequent theorem. Okay, so let's prove this one. So what's this statement says? For every n in natural number, okay, we will consider closed interval. Okay, so let's consider closed interval. Let In be a closed and bounded interval. So say from AN to BN. So closed here means the square bracket, right? Strip, not strip, but inequality. And bounded here meaning AN and BN are not infinity. They are not infinity. So I should say, maybe I should say AN, BN in R. Okay. So suppose, so I want to do nested. What does nested mean? Not Nestle, but nested. And you know Nestle is already increased price. Want to increase price. Milo is getting more expensive now. Okay, yeah, that's the news. So what nested mean? Nested. Nested is like nested. What does nested mean? Nest is what? Nest. Nest is what? Bird nest. Something you put at that. Okay, maybe yeah, your house. Anything like a house, right? So nest. What does nest next? What does nest do? Cover the bird, right? For example, bird nest. Okay, so you want to cover something. Okay, so let's see how we cover this. So suppose that AN plus 1 is covered by IN. Okay, so meaning you have a smaller, so you have an interval, you have a smaller interval. IN plus 1 is a subset of IN. So you are nested for each n. So how you imagine this? So you have I1, right? And then I2, and then I3, and then I4, something like this. Okay, and so on, nested. Okay. So you can think I1 is a nest of I2, I2 is a nest of I3, and so on. And you can see that because you could be equal, right? Here doesn't require you not equal, so we need to put an extra condition here such that the length of Bn minus An of In converges to 0. Okay, so that In is really getting smaller, shorter and shorter. What happens here? Converge to 0. Okay, what can happen? Can you guess what happened? Mathematics is like this. 你要有一个先入为主，可能有时候先入为主不好，但是呢，你先入为主过后，不是你会察觉到自己和别人的差别。Okay, instead of you just take in information， 因为你一直吸收 information 啊，你没有你自己的一个主见，不是你很难走你自己的路，你只能够听别人讲的。Okay, so if you want to work out your life， 你要走你自己的路，你要以后你的生活你自己掌管的话，你就要有一个先入为主的概念 ，and then try and compare 这个 view 跟别人的 view 什么不同。Okay, so let's say 我有一个 interval 越来越小，越来越小，越来越小，什么事情会发生？很多事情会发生啊，对不对？所以你猜一下，什么事情会发生？什么 ？Milo 会涨价 ？Okay, even this is false Milo still 涨价。Okay, okay, yeah, sure, 非常好。So, can you say something about points in IN or not? Yeah, points in IN. Sure, number of length decrease. Okay. Can you say about points in every IN? Every one. Yeah, so there exists. They don't just exist. It's a unique one. Unique point X in R such that this point is in every interval. Make sense or not? Make sense or not? It's like you taking limits from both sides. And then you see the limit is like pyramid like that, right? Converge to one number. And then this number should live in every IN. Okay or not? Okay, so how we gonna prove this? So how many things we need to do here? We need to first find this point. Okay. After we find this point, we need to show that this point is in every IN. And then there's only one such point. Okay, about 3 things we need to do. Okay, existence of this point, and then this point really lies in every N, and then it is unique. 3 things we need to show. 3 tasks. Okay, 3 tasks we need to do here. Okay, only one sentence, but I got 3 tasks. Okay, so very important. So when you listen to what people say, it's very important. Maybe one sentence got a few things going on there. Okay, 3 things you need to do here. Right, so how we find this X? Okay, let's see how we find this X here. So proof. So just now I mentioned something about a tri-pyramid thing, right? So we need to somehow find this limit. Okay, how to find this limit here? Okay, by using what we have known. So you see, what does a nested interval tells you? A nesting interval here telling you how you compare this endpoint here. How do you compare an plus 1, bn plus 1, bn? How do you compare them? If you have a nested intervals here, how do you compare them? So you know what is this an, bn? An, bn is the endpoint of in. An plus 1, bn plus 1 is the endpoint of in plus 1. So how do you compare this term here? No. I mean, which one is greater, which one is smaller? Compare numbers. Which one is greater, which one is smaller? AN, BN plus 1 should be both greater than AN plus 1. How about AN and AN plus 1? Can you compare? You want a nested effect of? You should have AN less than or equal to N plus 1. Cannot be greater, right? Greater, then you have something like this already. Correct or not? It's not nested already. Can you sit in a smaller house than you? Right. Okay, the house should nest you. Correct or not? Okay. How about AN plus 1 and BN plus 1? Because they form an interval, right? So BN plus 1 should be greater or equal to AN plus 1. Similarly, BN should be greater or equal to BN plus 1. Okay, otherwise you won't have nested effect. Okay, for ON. So in this case, what did you observe here? Can you observe anything? For ON, this inequality is true. Meaning what? AN form a sequence, BN form a sequence of what? What sequence is this? AN less than equal to BN plus 1. The next term is always greater or equals to the previous term. So this is a what sequence? Yes, this is a monotone. More precisely is what? Is a non-decreasing sequence. Okay. How about BN? BN is the other way, right? BN is greater or equal to the next term. So it is a non-increasing. Okay. In particular, they are monotone, like what Joshua suggested. So monotone, right? Just now say monotone bounded sequence converges. Okay, so if we have boundedness, then we might find some limit. Okay, so try and see whether they're bounded or not. Are they bounded or not? Bounded or not? Bounded by what? Bounded by Bn. N is changing. But we want to fix one real number, right? Sorry? Furthermore, the sequence, both sequence is bounded above by B1, correct? You have the largest house when n equals to 1. Okay. Bounded below or not? Okay, 1, yes. Okay, because the largest house is the I1. Bounded above by B1 and bounded below. Okay, so both of them are bounded above and below. So what do I say? What do I want to say here? Furthermore, this is true, implies that AN and BN are bounded. So this one is true for all n. Right? Okay, so they are bounded, they are monotone. So meaning what? Therefore, by monotone convergence theorem, they converge. So if they converge, right, we can talk about their limit. Let's say AN goes to A, BN goes to B. In particular, this A and B are some real numbers. Okay. Okay, they converge to A and B. Should they be the same or can they be different? Intuitively, they should be the same, right? Okay, so let's show it. It is the same actually. So how do we show A and B is equal? Here, we can use a limit law. So note that Bn equals to An plus Bn minus An. Okay, so this is the frequent tricks we use in analysis. Add something extra, but this something is very useful. Okay, Bn equals to An plus Bn minus An. So how do we use limit law here? We know that B goes to Bn goes to B. An goes to A. What is Bn minus An here? Why? Why 0? Yes, this is given by assumption. So that's why you have the assumption that the length of In converge to 0. So this one goes to 0. So by limit law, sum of convergent sequence, we get B equals to, so here by limit law, we have B equals to A plus 0, which is A. B equals to A. Okay, so we know that this two limits are the same now. Okay, now we want to show that this is in In for every n, and also this is the only guy that do that. It's unique. Okay. All right. So not bad. A is in this one, which is what we want, In. Okay. Why? Yes. An is less than equal to the sup of An and An such that n is in n. And this sup is exactly the limit we found, A. And similarly, it is equal to B, where B is the infimum of Bn. Okay. Why is this inequality enough to mention about this membership here? Because this is how we define the interval. How do we define the interval? So let me write down by definition. By definition, x in An or Bn if S in R such that S is less than equal to Bn and greater equal to An. Okay, so this is the inequality we want. Okay, for A to stay with the In. And we want to show that this is the only guy that do this. Okay, how do we show that this is the only guy? Let's say there's another guy that do it, right? Okay, so conversely, let's say we have other guys, call it X, that do the same thing. We want to show that this X is actually A. Okay, we want to show that X is actually A. What do we have? For this case here, we have that S is greater or equals to An. Okay, meaning what? This is an upper bound for An. Meaning what? In particular, this upper bound is greater or equal to our least upper bound. Make sense? Because the least upper bound is always less than or equal to other upper bound. This is the first definition we introduce. Okay, which is equal to A, right? On the other hand, what? Because S is always in this set, right? S is also always less than or equal to Bn. So what? In particular, this S is a lower bound for Bn. So I can use the same similar argument, says that X is less than or equal to the greatest lower bound. Right? This is the dual definition. But what is this increment? This increment is equal to B, which is equal to A, just now we showed. So all together we get what? A is less than equal to X, X is less than equal to A, which implies that the only points that live in all the interval is just A. Okay or not? Does it make sense? Following? Question about this? Question? Oh, question? No? I see you are quite excited at first, but suddenly become lost. Any question about this proof here? Why we have supremum? Because our AN is non-decreasing. Okay, VN is non-increasing. Okay, so one go top, one go bottom. And then you can consider the sup of AN, the increment of Bn. Right, and then they are the same. We show that B equals to A. And then suppose there's another guy that do this. Okay, and then we show that that guy have to be greater or equal to A and less than or equal to A. So it has to be A. Yes. X is greater or equal to sup. So at the top saying what? X is greater or equal to AN for all n. Means what? S is a upper bound. So sup is what? Least upper bound. The smallest amount of the upper bound. So the smallest one must be less than or equal to any upper bound. This is the definition of this. Similarly for infimum. Okay, infimum is the greatest lower bound. So it must be greater or equal to all the lower bound because S is one of the lower bound. Okay. Yeah, so by trichotomy law, X can only be A. Anti-symmetry, sorry. Yeah, sorry. Anti-symmetry. Yeah. Okay. Okay, any question? So we're going to use this proof for later for a very big proof, which we call the Bolzano-Wilson theorem. Very cool theorem. That's why there's a name on top of it. Bolzano-Wilson. Okay. Yes.
What's the
Yeah.
this
Ah.
and the left right?
Limit. How is it similar? What do you mean by left right limit? Function.
The limit.
Yeah. Yeah. So what I'm not sure why are they related.
Oh,
Really? Because we are not talking about function now. We are just talking about interval. Okay, interval. Why you would think of that? I don't know. I don't know why you think about the left right. Because you have a left right sequence. How do you talk about the? I'm not sure how to think about that. Maybe you can try and formulate further. Yeah. Any other question? Any other question about the proof? Okay, so try and go back while still fresh in your mind. Try and write down the proof. Okay. If I haven't posted up even, right, you can look at the books, the textbook I share you. Okay, try and copy down the proof. Okay. And we will see you tomorrow.